Oh my goodness, thank you. Sorry about that. Ah, geez. Can you hear? You should be able to hear me now. I had the mic on mute. Okay, let me just repeat what I said. Um, okay, guys, I apologize. Let me just repeat what I said there. Uh, and there we go. Okay, so basically, just very quickly, all I said was that this is the a lecture for Physics 102. It's actually a review session, Physics 102, April 1st. It's a continuation from our review session on Monday, March 30th. Okay, and if you go to our Moodle site, I've already logged in, and you go all the way to the very bottom there. Okay, well, oh no, I lost the capture. Hold on, I'll get it back. This happens every once in a while. Okay, so let me just show you that again. We were in our Moodle site here, and if you go all the way to the bottom, you could see the um, the 4 links there to our lectures from March 18th through March 30th. Okay, the last one is extra long. It's about 2 hours and 15 minutes, but it covers all of thermodynamics, and that's all. That covers all the material that's on the test. Then there's also the summary for uh, the for test 2, and we started on this. We actually got through points 1 through 4, and so today we're going to try to get through 5 through 10. I don't know if we'll make it, but we'll try. And well, let me switch to my whiteboard and we can begin. Okay, so let me see if the chat here, we can hear you now. Yeah, I had the mic on mute because I didn't want any background noise. Okay, so all right, let's begin. So we were working with waves, and point number 5 is on sound. And so there's two things about sound. One is the inverse R squared law, and the other one is intensity. And this piece right here, I just copied and pasted it from our review notes. Okay, and so what is this inverse R squared law? It's a pretty simple law. It basically says that the intensity, now this is the intensity measured as a linear quantity, that is as watts per meter squared. Okay, that intensity, it actually falls off as 1 over the radius squared. Now you could use this formula here, but you could just do it intuitively. And you know, if you have a certain intensity and you double the distance, you double R, what you will find is that I drops by 1/4. Okay, and if you triple R, I drops by 1/9, and if you quadruple R, I drops by 1/16, and so on. Okay, and you go, well, where did that 4 come from? Well, that 4 is 2 squared, and where did the 9 come from? That's 3 squared. So basically, that's the 1 over R squared. Okay, so if you double the distance, you quadruple the reduction in your intensity. All right, so uh, let's start off by looking at I before we look at beta. So I is the intensity, but it's the intensity measured in just ordinary units. That is watts per meter squared. Okay, and watts per meter squared are just linear units. They add normally. So this example, it's actually quite a trivial example. I said, you know, you got 2 sound sources. One sound source is 0.5 milliwatts per meter squared. A watt per meter squared is pretty big. So usually you work in milliwatts per meter squared. So you have one sound source at 0.5 milliwatts per meter squared, and another one at 1.5 milliwatts per meter squared. And what's the total? Well, you know what? I is just plain old add. Okay, so you just add 0.05 plus 1.5 to get a total of 2 milliwatts per meter squared. Nothing mysterious about I at all. And if you apply the inverse R squared law to I, the intensity, it just drops off this way. So here I have an example. If I have an intensity of 0.5 milliwatts per meter squared at a distance of 2 meters. What's the intensity at 4 meters? What's the intensity at 6 meters? Okay. Now, you know, rather than using this formula, let's just do it intuitively. If you're at 2 meters and you go to 4 meters, well, how much did you increase by? Well, you increased the radius by a factor of 2. That is, you doubled R. Now, if you doubled R, what happens? If you double R, the intensity decreases by 1/4. So if you go from 2 meters to 4 meters, you're doubling R, your intensity will go to 1/4 of the original intensity, and that means that you would have an intensity of 0.125 milliwatts per meter squared at 4 meters. Okay. If, however, you go from 2 meters to 6 meters, ask yourself, well, how much did you increase R by? You increased R by a factor of 3. That is, you tripled R. But if you triple R, It's not 1 over 3, it's 1 over 3 squared. That's 1/9. So I will decrease to 1/9 of its original value. And if the original value was 0.5, divide that by 9, you're going to get 0.056 milliwatts per meter squared. Okay, so there's the inverse R squared law applied to intensities measured in watts per meter squared. Okay, so very easy, nothing at all mysterious. Just looking at the chat here, I don't see any questions. If you have questions, remember there's a 30-second delay. Just ask the question. I'll eventually see it, and then even if I have to go back to a previous question, I'll go back, but otherwise I'm just going to move on. Now, you might say, well, all right, fine, we've got this I like that. Why would we want to introduce a different way of measuring intensity? Why would we want to introduce this log scale for intensity? And the answer is that intensities, especially intensities that we can hear with the human ear, span very, very large orders of magnitude. They go from very, very quiet, like 10 to the minus 12 watts per meter squared, all the way up to almost like a tenth of a watt per meter squared, which is a huge range. Okay, and so when you've got this huge range, from the very, very small to the very, very big, you go, well, how do you put everything on the same, sort of on par? And to give you an idea, in the lecture, I gave you this example where you have like millions and billions. Okay, so if you have $1 billion and you add a million to it, you're still really just a billionaire. Okay, because that $1 million is only like 0.1% of the billion. Okay, and yet a $1 million might be a lot if you're comparing it to 1,000. And so sometimes you're not so worried about whether you're talking about a billion or 2 billion or 3 billion or something like that. You're really more interested in the number of digits, okay? In the number. And so the log basically counts the number of digits in your number. This is log to the base 10. I didn't write base 10 everywhere, okay? So in order to get very, very large numbers and very, very small numbers all onto the same scale, use this log scale, okay? And so this is the usual linear scale in watts per meter squared. This formula allows you to convert it into this log scale. Okay, there's this I naught, but you almost never have to use it. It's just a reference intensity, and usually for sound it's chosen as 10 to the minus 12 watts per meter squared because that's the quietest possible sound you can hear. Okay, now the advantage of beta is that it allows you to put very loud and very quiet intensities all on the same scale because you can go from very, very small to the very, very large. But the disadvantage is that betas simply do not add. Okay? And here's an example of a wrong way of doing something. Suppose you have one sound source and it's only 40 decibels. That's pretty quiet, okay? And then you have a second sound source which is 50 decibels. You might say, oh, if to get the total, all I have to do is add 40 and 50 to get 90. That's wrong. That's not the way it works. Eyes work that way. Eyes will simply add, like I showed up here. The total, you just add up the eyes. But betas do not simply add that way. So this is wrong, okay? And so here's an example to show you how this works, okay? So if you have that, say an alarm, like a, I don't know, say, just a clock alarm. And one clock alarm generates a sound of 60 decibels. I'm going to ask you, what is the intensity in decibels for 5 of those alarms? Okay, what's the intensity going to be for 25? What's the intensity going to be for 125, 625, and so on? And you might say, well, where did you get this number 5, 25, 125, and so on? Well, 5 I just picked, but 25 is 5 times 5. And 125 is 5 times 5 times 5. And 625 is 5 times 5 times 5 times 5, and so on. Okay, so basically I'm saying, how much is it for 1? How much is it for 5 times more? How much is it for 5 times more of that? 5 times more of the previous one, and so on. So every time we're going up by a factor of 5, okay? Well, the way you answer this question is you start off with this, okay, where beta 1 is the intensity in decibels for just one alarm, okay, and I told you that was 60, okay. I1 would be the intensity for one alarm, but in watts per meter squared, okay? And so this one is in decibels, that one's in watts per meter squared. You could plug in for 60 there, you could plug in for I naught and solve for I1, but there's a much easier way to do that, okay? So if this is true, just keep that in mind, put that to the side for a minute. Take a look at this equation, and this equation says, okay, what's the intensity for 5? alarms. Well, it's going to be the same formula, but now instead of I1, I'm going to have I5 here, where I5 is the intensity of 5 alarms. And 5 alarms is just I plus I plus I plus I plus I. In other words, it's 5 times I1. Why? Because the I's, intensities in watts per meter squared, they just plain old add. So if you have one of them, it's I1. If you have another one, you have another I1. If you have then 3, then 4, then 5, you have 5 I1s. Okay, so we're going to replace this I5 with 5 times I1. And I'm going to write it this way on purpose. Okay, and that's a multiplication there. I explicitly wanted to show the multiplication sign. Okay, so it's not like a variable x or anything. So take a look at this and you go, well, why did you write it that way? And the reason is that the log function has this property that it turns multiplication into addition. Here's the property. Okay, so there's the property of the log function. So if you first multiply a times b and then take the log, that's exactly the same as taking the log of a, taking the log of b, and then adding them. Okay, so notice that the log, when it distributes over a and b, converts the multiplication to an addition. Okay, so I'm not going to prove that, but you should have seen that in an earlier math course. Okay, now why is this useful here? Well, you see that multiplication, it's going to turn into addition, and so I'm going to take out the 10 in front. All right, and I'm going to have log of the first number plus, because the multiplication gets turned into a plus, just like it did here, okay, plus the log of that number. All right, so basically I distributed the log over those two factors, and they became log of 5 plus log of I1 over I naught. Now let me bring in the 10 again. So then I've got log of 10 log of 5 plus 10 log I1 over I naught. Now if you take a look at this, that's the intensity in decibels that we started with. That's just this all over again. Basically what I did is I just teased out beta 1. Okay, and to be explicit, I wrote it right there. All right, actually, let me bring this to the next line here like that. Okay, so this is just the same as the original intensity beta 1, and this is the extra because you have 5 of them. Okay, well, you can easily do 10 log 5 on your calculator. It turns out to be 7. It's actually 6.989 something, but we'll just round it off to 7. You originally had 60 decibels, and so your total is going to be 7 plus 60, so that's 67 decibels. So 5 alarms has an intensity of 67 decibels. 1 has 60, 5 has 67. Okay, so let me look in the chat here. I don't see any questions, so let me move on. Okay. And let's do it for 25. Well, it's the exact same procedure as above. This time instead of 5, though, you have 25. Factor that out. There it is there. Log of 25 is 14. And so your intensity for 25 of them is going to be 60 plus 14 or 74 decibels. By the way, that log of 25, I know that's 14. And you go, well, how do you know it's 14? I didn't even need my calculator, okay? You go log of 25. You can write that as log of 5 times 5. Well, 10 times log of 5 times 5. So that's 10 of log 5 plus 10 of log 5. But notice that 10 of log 5, we actually worked that out before. And 10 of log 5 turned out to be 7. So that's 7 plus 7 or 14. So log of 10 times 25 is basically twice 10 log of 5, which is 7 plus 7 or 14. Okay, now I'm not going to do this for 125 and so on. All you would have to do is change that 25 to 125 in there and go on. But let's just notice a pattern here. If you have 1 alarm, you have 60 decibels. Okay, if you have 5 alarms, it's 67. You have 25, it's 74. Well, let's notice a pattern. Under the number of alarms, you go 1, then you multiply by 5 and you get the next one. Then you multiply by 5, you get the next one. You multiply by 5, you get the next one, and so on. So every time you go to the next level here, you're multiplying by 5. But if you take a look at the decibels, you have 60. To go to 67, you add 7. To go to 74, you add 7. To go to 81, you add 7. To go to 80, the next one, you add 7. So basically, every time you multiply by 5, it's just like adding 7 decibels. Okay? So the reason the whole decibel thing is used is because it basically changes something which grows very fast. You know, this actually grows exponential. Each time is 5 times more than the previous one. It changes it into something which just grows linearly. And in this case, it increases by 7 each time. In fact, if you look at what we did here, All right, you can actually reduce this formula. I didn't give you this in the lecture, but you could just reduce this formula to this. If you have one alarm, it's beta 1. If you have n alarms, it's going to be beta 1 plus 10 log of n. And that'll give you the intensity in decibels. Okay, so let me look in the chat here. Okay, we have a question here on the test. Will we have a number like 5? Yeah. What I would do on the test is I would do something like I would say, look, one alarm has an intensity of a certain amount, and I might not go up by factors of 5 because we did 5s here. I could do by factors of 2, just like we did in the lecture, or I could do factors of 4, or I could do factors of 7 or whatever. Okay, and basically it's the same idea. I mean, this number would be different. So if you had 7 here like that, well, that number would be and I'm not going to pull out my calculator right now, but it would be more than 7 but less than 10. And so yeah, I would give you numbers. So to answer your question, yeah, I would give you numbers like 5, 25, 125, but I would do other factors, like maybe I would do 2, 4, 8, 16, 32. Okay, or I would do factors of 3. All right. So I hope that answers your question. Otherwise, just ask again, and I'll come back to it. Okay, let me move on because I want to try to get through as much as possible. The next topic we looked at, this is still part of sound. So one topic in sound was intensity. Okay, and for intensity we had the inverse R squared law, and we also had decibels. And for the other last topic of sound is Doppler effect. And the Doppler effect occurs whenever you have a receiver and a source. So the source is like something that's emitting sound, okay, like a car horn, okay, and the receiver is someone who's hearing the sound, okay, like maybe you're standing on the side of the road and you're hearing it. Now, if neither you nor the car are moving, so neither the receiver nor the source are moving, you would hear some frequency, F naught, okay, whatever that might be. Okay, but if either the source or the receiver are moving, you actually don't hear that frequency. You hear a shift in that frequency. And this is known as the Doppler shift or the Doppler effect. Now, if either the source or the receiver are approaching one another, okay, so they're getting closer together over time, the frequency that you would hear is higher than the frequency that's actually being emitted. All right. And you might wonder, why is that? Well, imagine that, probably the easiest one to picture is the source is standing still and you as the receiver are running towards the source. Well, if you weren't running towards the source, the crest would come at you at a certain rate. But because you're running towards the source, you're actually running into the waves. So you're shortening the amount of time that it takes one crest to arrive after another crest. And if you shorten the amount of time, you're going to get more crests per second. More crests per second, that's a higher frequency. Okay, so that's what causes this, and it's the same kind of thing if the source is approaching you. Okay, so basically the frequency shifts up if either the source and the receiver are approaching one another, and the frequency shifts down if they're receding from one another. Okay, so there it is. Now, the formula, the way I gave it to you here, it looks a little confusing because I have this plus minus minus and this minus plus, okay? And that's because you got to decide, do I use the plus or the minus on top, or do I use the minus or the plus in the denominator? And you can make a decision. You don't have to really memorize that, but you can make a decision based on whether you expect the frequency to be higher or you expect the frequency to be lower, depending on whether you're approaching or receding. Okay, so let me see here in the chat. It did answer my question. Okay, good. So all right. So here's a question on Doppler effect. Okay. All right. So for example, you're standing on the side of a road. Okay, so you're standing still, and a car is traveling away from you. In other words, it's receding at a velocity of 60 meters per second. Okay, if the car horn emits 500 hertz sound, what do you hear? Okay, so let's think about this. If the car is driving away from you, so the car and its horn are the source, if it's driving away from you, what do you expect, higher or lower frequency? Well, when the source is receding, it's getting further away, you expect a lower frequency. Okay, so let's write down what we know. In this formula here, we know V by itself, there's a VR, that's the receiver and Vs is the source, okay? But V by itself, that's the speed of sound, okay? And I don't expect you to memorize that. It's not a hard number to memorize, but I give you constants, okay? So the speed of sound is 340 meters per second, okay? And the receiver, that's you, okay? Because you're not emitting the sound. The car is emitting the sound. Well, its horn is. And you're standing still. So you as the receiver, the velocity of the receiver is 0 meters per second because you're standing still. And the car, it's moving at 60 meters per second, and there it is, okay? And now you use this formula here, and you have to make some decisions. Well, first, in the numerator, your velocity is 0, so you don't have to worry about the plus or minus there, because plus or minus 0, whether you add 0 or subtract 0 from a number, you still get that same number. So here you don't have to make a decision, but here you do have to make a decision, because you've got the velocity of sound, which is 340, and then you've got the velocity of the source, which is 60 meters per second, and you've got to decide, like there I've given you the answer, it's plus. You've got to decide, do I need a plus there or do I need a minus there? Well, if you were to put a minus there, that would make the denominator smaller, and it would make your number bigger than the 500 hertz. But you expected a smaller number, so that's wrong. You have to actually do the plus there like that, okay? So I'll go through that one more time, but let me just show you how I substituted in everything here. So the frequency that you would hear is the original frequency, that's the 500 hertz, times the speed of sound plus or minus the speed of the receiver. Well, the receiver isn't moving, so the speed of sound plus or minus 0 is still just the speed of sound. There it is, 340. Then divided by, okay, and now we're in the denominator, here it is, and it's the speed of sound, okay, plus or minus, so you don't know what that is quite yet, and your speed, the speed of the source, which is the car, is 60, okay, and you have to say to yourself, do I expect this number, I want this number to be bigger or smaller than 500? Well, you want it to be smaller, because when the source recedes from the receiver, you expect a lower frequency. If you put a minus there, that would be wrong. You would get a higher frequency, so you put a plus there, and you get the answer of 425. Okay, so let me see if there's any questions in the chat. Nope, not yet. All right, there you go. Okay, so that's how you solve that one. All right, now if you were to change the receding to approaching, then it's exactly the same, but you'd put a minus there and you get a higher frequency. Okay, second example. This time the car is standing still, okay, and you're receding at 60 meters per second, okay? So 340 meters per second for the speed of sound. Speed of the receiver, 60 meters per second. By the way, that's extremely fast, but it's just a problem, okay? And the source is standing still, so the car is just standing there with its horn blaring, and you're driving away from it at 60 meters per second. What would you hear? Well, here's the formula. Okay, so for the original frequency, 500 hertz, okay, over here, you're going to have, let's put a little question mark in there for now, okay, you don't know what sign you need, but you're going to have the speed of sound, there's the 340, you're going to have the speed of the receiver, 60 meters per second, and do you want this to be smaller or bigger than F naught? Well, you're receding, getting further away from the car. You're driving away from the car at 60 meters per second. So you want this to be smaller. To be smaller, this time it has to be a negative, okay? So when it's in the denominator, to get a smaller number, it's a plus, but in the numerator, you're going to need a minus, okay? And so you do 340 minus 60, and in the denominator, divided by the speed of sound, plus or minus the speed of the source. But what is the speed of the source? 0. So it doesn't matter. You don't have to make any kind of decision to plus or minus. Work that out, and you'll find that it's 412 hertz. Okay, so this is kind of interesting because when the car is receding from you, you hear 425, but when you're receding from the car, it's actually a different frequency. Okay, so the Doppler effect in air is not symmetrical. All right, so that's basically it for the Doppler effect. And let me see if there's any questions in the chat. There are no questions. Okay, so let's move on. All right, so we're on number 7 here. Number 7 is thermometers. And for thermometers, we had this formula right here. This is basically an approximation that allows you to make thermometers. And what does it say? Okay, so physically, what does it say? So basically, this is saying, look, if you have a change in temperature with some material, then it's going to expand or contract. And if it expands or contracts, well, then there'll be a change in length. Okay, so basically, a change in temperature causes a change in length. So I mean, you know this, like like you have that aluminum door that in winter it opens and closes just fine, but in the summer it doesn't quite close, just doesn't close right, and you wonder what happened. Well, it expanded, and the reason it expanded is because in higher temperatures the material is actually bigger. And you say, well, is there a formula for that? Yeah, this is actually an approximation, but it's kind of a good enough approximation. It basically says that the change in the length of something is linearly proportional to the change in the temperature. Okay, and what goes into that constant of proportionality? Well, one is the original length. The reason you have the original length in there is because the more material you have, the more expansion and contraction you can get. Okay, but there's also this alpha, which is the coefficient of linear expansion and linear thermal expansion, and that just depends on the type of material, and it's a constant I would have to give you, unless maybe I'm asking you to calculate it for some material, but there it is. Okay, so why is this used for thermometers? Well, because that's how you calibrate a thermometer. Like thermometer could be made out of something like alcohol with a little bit of food coloring in it, and at 0 degrees Celsius you put a little tick on the side of the glass, and you say, well, that's how long it is at 0 degrees Celsius. And then at 100 degrees Celsius, that's where water boils. You see how long it is, and you put another tick. And the two ticks, they've got some distance between the two, and you cut that up into 100 pieces, 100 equal pieces, and ta-da, you've got the Celsius scale. Okay, so here's an example. Let me see if there's a question. No, no questions. Okay, so here's an example. Let's say we have a lower temperature of 20 degrees Celsius. That's basically room temperature. And we heat an object up to 40 degrees Celsius. Okay, so we're going from 20 to 40 degrees Celsius. And I give you this coefficient of thermal expansion. There it is. Now, usually those numbers are really small, okay? And the units are kind of funny. They're reciprocal degrees Celsius, and you'll see why when I do the problem, all right? The original length of this bar, whatever it might be, this material, I said it's 1.5 meters at 20 centimeters. That original length, that's your L naught right there. Okay, so that's the original length. And I want to know how much does it expand? Okay, and that's your delta L. Well, I mean, it's pretty trivial. You just plug in the numbers here. So delta L is equal to, here's my alpha, here's my L naught, the length at the lower temperature, and here's my delta T. Well, I started at 20, went up to 40, so 20 minus 40 is 40. And you multiply this all out, and you're going to get that it's 0.015 meters, okay, like that, or 15 centimeters, okay? Let me just show you very quickly that the units work out. The delta T has units of degrees Celsius. The alpha naught has units of per degree Celsius, so that unit there will cancel against this unit there, and all you're left with are meters, okay? So, and delta L has to be in meters, okay? So there you go, it worked, all right? And so basically this bar has a length of 1.5 meters at 20 centimeters, and it's going to grow by 15 centimeters when you get to 40, so it'll be 1.65 meters at 40 degrees Celsius, okay? So, I mean, it's not a very deep formula, but, it's the formula that's used to calibrate thermometers. All right. Now, this formula is a little bit deceptive. It's an approximation. Not all materials will expand linearly over large temperature ranges, okay? So what that means is that if you have, say you're using alcohol as your thermometer, and then you're also using mercury as your thermometer, if you make them agree at 0 and 100 degrees Celsius, because you simply calibrated it to agree at those two temperatures, you'll discover that if you're at 50 degrees Celsius, the two thermometers won't quite agree. And you go, well, what's going on? Why do they agree at 0 and 100, but they don't agree in the middle? And the answer is, you made them agree at 0 and 100. And they don't really expand linearly. The material doesn't expand linear. It might expand a little faster at first and then it slows down, or it might expand a little slow at first and then speeds up. Basically, it's almost like alpha has itself a temperature dependence in it. Well, if alpha has a temperature dependence in it, then you haven't isolated the temperature dependence, and you really can't use this to make a thermometer. But luckily, there is one class of materials where the expansion is linear over large temperature ranges, okay? And those are the ideal gases. Okay, so there we go. These are ideal gases. There's two forms of the ideal gas law, and it's PV equals nRT, and PV equals nRT is basically the way you would have seen it in high school, okay? And R here is that ideal gas constant, and N is the amount of material, the amount of gas present, but as numbers of moles, okay? So it's PV equals nRT, all right? But that's kind of popular in chemistry. In physics, this other form is more popular. PV is equal to capital N, where capital N is literally the number of particles in the gas. Okay, so it's like the number of atoms or the number of molecules. Like you literally would count them. All right, and T is the temperature. The temperature, though, in both forms, the temperature has to be an absolute scale, because remember, this is in the context of thermometers. And I know for the thermometer we use delta L, but the equivalent of delta L here is V. And think about this: as your temperature gets colder and colder and colder, what will happen is your V will shrink. Well, at the point at which V actually becomes vanishingly small, in other words, V is 0, if the pressure stays constant, N stays constant, K Boltzmann is just a constant, which I'll give you in a second. So if P is constant, N is constant, and KB is constant, then when V is 0, T is 0, okay? And you say, well, when does that happen? Well, the velocity, not the velocity, sorry, the volume will be vanishingly small at absolute 0, okay? And so in both of these equations, the temperature has to be measured in Kelvin, not Celsius, okay? Because you got to get the 0 of the scale right. And to convert from Kelvin to Celsius, you've probably done this in other classes. Basically, you take your temperature in Celsius, you add 273, and you get your temperature in Kelvin, okay? This just does not work at all in Celsius. Imagine if it did. At 0 degrees Celsius, okay, at 0 degrees Celsius, that's the temperature at which water freezes. Well, at that point, any gas, all gases would have 0 volume. That means that when water freezes, which happens on Earth quite often, our atmosphere would freeze too. Okay, and that just doesn't happen. Okay, our atmosphere, oxygen, nitrogen, and so on, it would acquire a negligibly small volume, not at 0 degrees Celsius, but at negative 273 degrees Celsius, or absolute 0. Okay, so basically the summary there is that for both of these equations, the temperature has to be in Kelvin. Okay. Now, usually for Physics 102, I didn't do it this year because of the unusual circumstances. I usually derive that equation from Newton's laws. It's rather remarkable. It doesn't take a lot of work. You can actually prove that PV equals NK Boltzmann T starting from Newton's laws. Okay, and that's kind of amazing. If you do, you find there's a really remarkable relationship that the average kinetic energy of the particles, okay, now some particles will have more kinetic energies, others will have less, but on average they'll have a certain amount of kinetic energy. So the average kinetic energy of the particles is equal to 3/2 times K Boltzmann, which is just a constant, times the temperature. Okay, so never mind the 3/2 and the K Boltzmann, because that's just a number. Think of it like a conversion factor, from Kelvin to joules, because this is in Kelvin and that's in joules. You know what this basically says? It basically says, you know what the temperature is of an object? The temperature just is the average kinetic energy of the particles. Okay, so that's kind of remarkable. In other words, when you touch something that's cold, you can basically say that the average kinetic energy of the particles of this cold object is low. And you touch a hot object, and you could say that the average kinetic energy of the particles in the hot object is high, okay, or they're moving fast. And then the other thing you can do is you can use 1/2, the average kinetic energy is equal to 1/2 mv squared. So given the temperature, you can actually say how fast the particles are moving in the gas, okay. So this is a rather remarkable result, and it really shows you what the ideal gas law is all about. The ideal gas law is basically about a bunch of particles that are moving around. They have a certain temperature, in other words, a certain kinetic energy, and at a certain temperature, aka kinetic energy, they have a certain pressure and a certain volume. Okay, so let's do some problems with this. We'll do 2 problems. Suppose we have a gas which is at 3 atmospheres. Okay, it starts off at 3 atmospheres with a volume of 5 liters and at a temperature of 50 degrees Celsius. Okay, so that's our starting point. And we're going to heat that up, or we're going to change that to a gas with a pressure of 2 atmospheres and a volume of 2 liters, and I want to know the temperature of the resulting gas. So basically, I'm lowering the pressure from 3 atmospheres to 2 atmospheres, and I'm decreasing the volume from 5 liters to 2 liters, like that, and I want to know what happened to the temperature, okay? And the other thing is that the amount of gas doesn't change. All right. Well, the first thing is you cannot work in Celsius, so you have to immediately convert that to Kelvin. 50 degrees Celsius is 50 plus 273. So that's 323 Kelvin. Okay. And now, if you wanted to use this equation directly and calculate, say, the number of particles so that you can use it in, a second part of the problem, well, then you've got no choice. You would have to actually convert 3 atmospheres to MKS, in other words, to pascals. You'd have to convert liters to cubic meters and so on. And so there's a much easier way to do this. And basically, since the number of particles, whether you're talking in terms of moles or the number of particles, since that's the same, okay, all you have to do is you could just rearrange this formula here, and you could set NR, which is a constant, equal to PV over T. All right. Now, if that's true for your initial state, P1 V1 T1, then it's also true for your final state, P2 V2 T2. And so you have to have that P1 V1 over T1 will equal P2 V2 over T2. Why? Well, because P1 V1 over T1, that's got to equal the number of particles times R. Okay. And P2 V2 over T2 has to equal, again, number of particles in moles times R. Okay. And so since the number of particles doesn't change, you must have this relationship PV over T remaining unchanged when you go from one to the other. Now, why do it this way? Why not, just solve for N and then plug back in? Well, because then you don't have to convert. You see, if you just plug in for P1, 3 atmospheres here, and for P2, 2 atmospheres here, look at that. The atmospheres here, and atmospheres here, they just cancel out. So that makes life a lot easier. And the liters here and the liters here just drop out. This is 323 Kelvin, and then you can solve for T2. And if you do that, you find that T2 is equal to 86.1 Kelvin. Okay, so just an easier way to solve these kinds of problems, where you start with one state, P1 V1 T2, and you go to another state, P2 V2 T2, like that. Okay, so let me see if there's any questions in the chat. Nope. All right. So now the next one I ask, how many particles are in this gas? Okay. And to solve for that, we're solving for N. So we're going to use the second form. Okay. That one will give it to you in moles, but this one is better for number of particles because you've got capital N. And so we'll just take this and we'll rearrange it to get this. Okay. So I divided both sides by K Boltzmann times T. So now you must convert the units, because otherwise things are not going to work out correctly. So P is 3 atmospheres, but an atmosphere is 101.2 kilopascals. Whoops. 100 kilopascals. Whoops, I think I made a mistake in this problem. Yeah, I did. I'm off by a factor of 2 here. So that's 3, that 5, 7 there should be 5. Okay, and well, now it's correct. Okay, so there we go. That's correct. All right, and then that converts the pressure from atmospheres to pascals. All right, now the volume is in liters, and you have to convert that liters to cubic meters. Well, 1 cubic meter is 1,000 liters, and so 5 liters, divide that by 1,000, it'll give you the answer in cubic meters. Okay, and now if you substitute in here, so that was off by a factor of 2. So here I've got the pressure in pascals. Here I've got the volume in cubic meters. This is Boltzmann's constant, KB, in joules per Kelvin. Okay, and that's the MKS units. You can see it up here. Okay, so K Boltzmann is 1.38 times 10 to the minus 23 joules per Kelvin. All right, so there it is there. And then you get this. And I'm not even going to do this on your, I didn't even actually solve the answer, but you can do this later on your calculator. But basically, the number you should get is roughly 1 mole, okay, approximately 1 mole, somewhere around 10 to the 23, maybe 10 to the 22 or 10 to the 24, I don't know, but somewhere in that region. But basically, this is the correct approach there, okay? So, if you're just going from P1 V1 T1 to P2 V2 T2, and you use this technique, you don't have to do any kind of fancy conversions. But if you're just going to use the ideal gas law by itself like that, well, then everything in there has to be an MKS, which means you're going to have to convert atmospheres to pascals. You're going to have to convert liters to meters cubed, and temperature, of course, has to be in Kelvin. Okay, so all right, that's part B to the problem. Here's part C. Let me see if there's any questions in the chat. All right, no questions so far. All right, so how much energy do these particles have at 323 Kelvin? Well, now we're back to this other amazing formula. Okay, right there. Basically, that the average kinetic energy of the particles in a gas is directly equal to the temperature with just this constant in front. Okay, so that's kind of, it really tells you what temperature is. All right, so all right, well, how much energy do the particles have at 323 degrees Kelvin? T has to be in Kelvin for this formula too, obviously. Okay, so we have 3/2. We'll write that as 1.5 right here. Okay, K Boltzmann, there it is in joules per Kelvin. There's the temperature in Kelvin. Work it all out, and it seems to work out to 6.69 times 10 to the minus 21 joules. Okay, and the last question I'm going to ask is, what's the average velocity? Now, to do the average velocity, you've got the average kinetic energy. And the average kinetic energy, you could just write as 1/2 mv squared, where v is the average velocity. It's actually not an average velocity. It's what's called the root mean squared, but you could think of it as the typical velocity of the particles in the gas. Now, you guys are probably biology or chemistry majors. When you talk about the size of atoms, like if I say an argon atom, you never in chemistry or biology, especially in chemistry, you usually don't talk in terms of kilograms. That's more of a physics thing. You talk in terms of atomic mass units, okay? And the atomic weight is basically just count up the number of protons and the number of neutrons in the nucleus, and that's your atomic weight. And the electrons are just fluff, so you can kind of ignore them. So within a good approximation, the argon atom has a weight of 40 atomic mass units. But you can't just put 40 in here, because that would be like 40 kilograms. So you have to convert it from atomic mass units to kilograms, and here's the conversion factor. Okay, so the conversion factor is 1.66 times 10 to the minus 27 kilograms per AMU, and you multiply that by 40 because that's the atomic weight of argon, and you get to 66.4 times 10 to the minus 27 kilograms. Okay, so we have the energy, the kinetic energy right there, because we solved it in the previous problem. The 1/2, there it is, 0.5. The mass in kilograms, the 66.4 times 10 to the minus 27. And we're solving for v squared, so there's v squared. And there's just some arithmetic there, and it works out to be 450 meters per second. And I know that answer is approximately right, okay? Because generally speaking, the velocity of particles in the air is roughly around the speed of sound, okay? And the speed of sound is 340 meters per second, and there you can see argon at 450 meters per second. By the way, we have quite a bit of argon in our atmosphere. Not a lot, but there's some argon in our atmosphere, okay? So there we go. Let's see if there are any questions in the chat. No, okay, guys. It looks like you guys are okay with this. So let me go on here. I think I'm only going to be able to get through specific heats because I've only got about 10 minutes left, but that's okay. The second law of thermodynamics is pretty easy, and I can just aim you to where I went over that with my Physics 112 class in their lecture. I can just, within the, I could just email a timestamp at which you could review that. But basically here with specific heats, you know that when you add energy to a substance, like, you put a pot of water on top of a stove, you're adding heat to that, all right? Well, it's going to heat up the water, okay? So the amount of energy you're going to add is going to equal some constant times the change in temperature. So the change in temperature is directly proportional to the amount of energy. Well, it does depend on some constant, and there's two things that go into the constant. One is how much stuff there is. It takes twice as long to boil twice as much water, to heat up twice as much water, okay? And it depends on the type of material. So if you're talking about, water, that's got a specific heat, or if you're talking about alcohol, it's got a different specific heat, okay? Now, this formula is okay when you're going from one temperature to another temperature, and the phase does not change. So if you start with the liquid phase, liquid water, you go to liquid water, that formula is fine, okay? It's even fine if you're from ice to ice. So you got ice at, say, minus 10 degrees Celsius, and you heat it up to ice at minus 5 degrees Celsius, that's fine, okay? But when you undergo a phase transition, that is, you change the material from a solid to a liquid or liquid to a gas, this formula doesn't work because during a phase transition, the temperature doesn't change. There is no such thing as ice at 10 degrees Celsius, okay? Because once the ice gets to 0 degrees Celsius and you keep adding heat, it doesn't become ice at 1 degree Celsius and then 2 degrees Celsius. Ice at 0 degrees Celsius at heat becomes a little bit of water and ice at 0 degrees Celsius. And as you add more heat, the amount of ice decreases and the amount of water increases until you get all water at 0 degrees Celsius. And then once you have all water at 0 degrees Celsius, if you keep adding heat, then the water will start to heat up. Okay, so these are known as phase transitions. And to calculate how much heat it takes to undergo a phase transition, there's no delta T, because there's no change in temperature. It's just how much stuff do you have and what's the latent heat, okay, of the material. So here's two examples, all right. How much energy is required to heat up 450 grams of water from 15 degrees Celsius to 75 degrees Celsius? Well, water doesn't change phase between 15 and 75 degrees Celsius. So you use the first formula, this one right here, okay, there it is. And if you substitute in, that's going to be M is 0.45 kilograms. C is going to be the specific heat of water, and I would give you this number. It's 4,186 joules for every kilogram and for every degree Celsius that you heat it up. And then the delta T, well, that's going to be from 15 to 75, so it's basically, 75 minus 15. Let me put the units in here for a second. Okay, and notice the units work out because that kilogram will cancel that kilogram, and this degree Celsius or per degree Celsius will cancel that degree Celsius, and all you're left with are joules. Run that through your calculator and you get 113,000 joules or 113 kilojoules. Okay, so that answers the question. How much energy to heat up 450 grams of water from 15 to 75 degrees Celsius? 113 kilojoules. Okay, now what if I asked how much heat does it take to melt 3 kilograms of ice? Okay, so basically what I'm saying now is, look, we have ice at 0 degrees Celsius and we have water, we have ice at 0 degrees Celsius and we want to melt it and make water at 0 degrees Celsius. No change in temperature, purely a change in phase. So now you have to use the second formula here like that, okay? And for that formula, you have delta L is equal to M, delta L like that, and M is 3 kilograms. Your L, I would have to give you these latent heats. There's two. There's the latent heat of fusion, and that's the heat to going between ice and water, latent heat of fusion, and that's the one we want. But there's also a latent heat of vaporization. You're going to have to decide which one you want. Latent heat of vaporization is to go from water to steam or from liquid to gas, okay? So here we're going between the solid and the liquid phase. We need the latent heat of fusion. That turns out to be 334 kilojoules for every kilogram of ice you want to melt. Well, you want to melt 3 kilograms of ice, so you multiply that by 3 and you get 1,002 kilojoules or 1 megajoule of energy. That's a lot of energy, okay? So, it's not easy to melt ice, all right? So there you go, okay? Let me just do one more example with this and then we'll call it quits. I know that I didn't do I won't be able to get to the second law of thermodynamics, but I'll give you a reference for where you can go over some questions for that. So here, this is another example. Let me actually put EG here because this is yet another example. We're going to take 250 grams of ethanol at 65 degrees Celsius. So this is ethanol, okay? And it's hot. 65 degrees Celsius is pretty hot, okay? And we're going to mix it with 200 grams of water at 15 degrees Celsius. So this is water which is kind of cool, about the temperature that it comes out of a tap, okay? And we want to know what's the resulting temperature. Okay, and you go, well, how does that work? Well, you heard me mention the second law of thermodynamics. There's a first law of thermodynamics, and the first law of thermodynamics says energy is conserved. Okay, so the heat that's going to be lost, or the energy, heat and energy, synonymous terms. Okay, so the heat lost from the ethanol, that's going to have to equal the heat gained by the water because energy is not lost. Okay, so if the ethanol gets cooler, it's losing energy, and the water is going to have to gain it because where else is it going to go? Okay, I'm assuming there's nothing out, nowhere else it can go. Well, then the heat loss from the ethanol is going to have to be the heat gained by the water. So here you say, well, how do I calculate the heat loss by the ethanol? Well, it's this formula here, MC delta T. But now you'll notice, and I know this is kind of ugly because I'm writing it in ASCII, but this is the mass of the ethanol times the specific heat of the ethanol multiplied by the change of temperature of the ethanol. Okay, that's the heat loss by the ethanol. That's got to equal the mass of the water multiplied by the specific heat of the water multiplied by the temperature change of the water. Okay, so now what's the mass of the ethanol? Well, I told you it's 250 grams or 0.25 kilograms. The specific heat of the ethanol, you have to look that up. It's 2,400 joules per, sorry, I forgot a little per there. 2,400 joules per kilogram degree Celsius. And the delta T of the ethanol, we don't know it. Okay, so I'll show you how to reduce that a little bit more later. The mass of the water, 200 grams is 0.2 kilograms. The specific heat of water, 4,186 joules per kilogram degree Celsius. And then there's also the change of temperature of the water. Well, the ethanol is cooling. So the delta T of the ethanol, is the higher temperature, which is the 65, minus the final temperature, which we don't know. Okay, so the delta T of the ethanol is 65 minus T. T is the lower temperature, that's the temperature it's going to go to, and 65 is the higher temperature. So there's your delta T for the ethanol. For the water, it's the other way around. Its lower temperature is 15, and it ends up at this higher unknown temperature, T. Okay, so the delta T of the water is the higher temperature T minus 15 degrees, okay? And so it's kind of backwards, but just think of it this way. You're always subtracting the bigger number from the smaller number. The ethanol cools, so the 65 degrees is going to be bigger than that final temperature T, okay? And T is, again, the resulting temperature of the mixture. The water, it's going to heat up, so its lower temperature is 15 and its higher temperature is T. So delta T of the water is T minus 15 degrees Celsius. We'll plug that in here for that, and you're going to get this formula. And now there's only one unknown. It's just a matter of solving for that unknown. And I just reduced it there, and then reduced it a little bit more, and then reduced it a little bit more. And the final answer I get is 35.9 degrees Celsius, okay? And ask yourself, does that make sense? Well, look, the ethanol starts at 65 and it cools down to 35.9 or 36 degrees. Let's round off, 36. The water starts at 15 and it warms up to 36. Yeah, that sounds about right. That sounds about right. They kind of meet, not quite in the middle, but they meet somewhere in between. And yeah, they meet at 35.9 degrees Celsius. Okay. You know what I've got? I know that technically the class ends right now, but let me just very quickly, I won't do a problem with this, but let me just quickly tell you what the second law of thermodynamics is about. The first law says that energy is conserved, but not all energy conserving processes are possible, okay? So work can produce heat, all right? That's easy. That's friction, okay? So when you rub your hands together, you're doing work. And where did the energy of that work go? It goes into warming up your hands, okay? But the opposite can't happen. You can't have heat spontaneously becoming work, okay? Now, if it did, imagine if it did, you could imagine that the room is at a certain temperature. If the room cools down, then what? Well, then that energy from the room cooling down could go into lifting something up, okay? Like lifting a monitor up into the air or my table up into the air. Well, that just doesn't happen, I mean, you don't have that magically the room will start to cool off, losing energy, and that energy goes into mechanically doing work and lifting up a table. So whereas work can spontaneously become heat, heat cannot spontaneously become work, okay? Similarly, heat cannot spontaneously flow from cold to hot. I mean, in fact, we saw that when we mixed the ethanol and the water together, okay? If you put a hot object and a cold object together, the hotter object will become cooler and the cooler object will become warmer until they reach, equilibrium. Never are you going to put, a hot object by a cold object, and the hot object gets even hotter and the cold object gets even colder. That doesn't happen, okay? It would conserve energy because the cold object might lose 10 joules and become even colder. The hot object would then gain those 10 joules and become even hotter, but it just never happens. It never happens, okay? And so heat cannot spontaneously flow flow from cold to hot. It can flow from hot to cold spontaneously, but not from cold to hot. And so this here is the second law of thermodynamics. It's often, another way to put it is that entropy is always increasing, and people sometimes say that entropy is time zero, and that's because the second law of thermodynamics is not time reversible. Okay, the second law of thermodynamics points forwards in time, but it does not point backwards in time. Okay, so if you reverse time, the second law of thermodynamics is broken. Newton's laws are actually time symmetrical. Okay, so if you ran a movie where you're watching two billiard balls clanking together, okay, and obeying Newton's laws while they collide with one another, if you were run that movie forwards or you run that movie backwards, you can't tell which one is physically correct and which one isn't. They're both physically possible. So Newton's laws are time reversible, but the second law of thermodynamics is not time reversible. Okay, so I'm going to leave this off because I've run out of time. But basically, you can take a look at. I'll give you a little timestamp for my other 112 where I did go over that. Okay, so well, that's it. I don't see any other questions in the chat, and I'll just wait another second. Another 30 seconds to make sure there are no other questions. But if there are no other questions, well then this lecture is over, and I'll leave it up online for you to watch. And like I said, I'll give you a timestamp where you can watch an example of me using the Carnot efficiency to calculate the maximum efficiency of an engine. All right, so no more questions, it looks like. All right, guys, this is it. It's the end of the stream, end of class, and we will have the usual hangout tonight, and you can ask any more questions then. All right, bye-bye.